Hi class. Today let's go together over this problem number 3 in the practice sets for module 4. Okay, so let's start by reading the problem. This problem is talking about a method to determine the flow rate of a part of the circulatory system by injecting a small meter amount of a radioactive tracer and then measure the concentration of the tracer in a sample of blood that's withdrawn a suitable distance downstream of where that tracer was injected. We know that in this particular case, a patient's bloodstream is composed of 95% blood plasma and 5% red blood cells, and the physician, in order to determine the flow rate of the patient's bloodstream, injected a radioactive tracer into the patient's bloodstream at a known flow rate of 17.21 grams per hour. We know that if later the physician took a sample downstream from where the radioactive tracer was injected, and we know that the tracer content at that point is 10%. We can assume that no reactions occur, therefore everything is conserved because nothing is generated or consumed, and that the flows are operating at steady state, meaning that everything should be equal to 0. So now we're asked to calculate the flow rate of the patient's bloodstream containing 95% blood plasma and 5% red blood cells. So basically the blood that came in at the beginning. And it asks us to give us the answer in units of milliliters per hour, so that seems important. Okay, so I'm going to start by highlighting all the information that I think is important. So in yellow, I'm going to highlight everything that is known. So we know that wherever the radioactive tracer flows at this rate, we know that the content of the sample downstream is 10%, and that's it. Then we also know the assumptions. So in purple, I'm going to highlight those. No reactions, which is great. And then steady state. And in blue, I'm going to highlight what we're asked to calculate. So we're asked to calculate the flow rate in that original stream. And we're asked to please give that in units of milliliters per hour. Okay, so step number 1, as usual, draw a system. So I'm going to draw this as a vessel, a blood vessel. And this is going to be kind of my system. And we know that we have the bloodstream coming in with 95% plasma. I'm going to call that PL. And 5% RBCs, red blood cells, okay? We also know that we have another stream coming in, which is that radioactive tracer. So we know that we have tracer here and nothing else. And I'm going to call this 1 and this stream 2 and the outgoing stream 3. And we know that that radioactive tracer, it flows, the mass flow rate of this stream is 17.21 grams per hour. Okay. And then in the outgoing stream, we don't know the concentration of plasma, unknown. We don't know the concentration of RBCs. But we do know that the mass fraction of tracer is 10%. We also don't know the mass flow rates here or here. Sorry, 1. Now, if we go back and read this question and read what it's asking for this problem, what essentially the problem is asking us to do is to calculate the mass flow rate in stream 1. That is all it wants us to do. Okay, so the next thing I am going to do is in this particular case, one thing I'm going to do is set up my accounting equations. So for the total mass, it would be M1 plus M2 minus M3 is equal to 0. And I'm going to do the same for every species. So for plasma and RBCs, it's going to be the same. So it's going to be something like this. Or this for red blood cells. And for the tracer, it is going to be, the tracer is only in streams 2 and 3. Okay, so now I get to decide where to go next after this, right? If I want to calculate the mass flow rate in stream 1. Okay, so essentially what I usually go to, and in this time I decided to write everything that's known or unknown directly on the diagram. Like I've said before, some people choose to do tables. I'm not going to do a table today, but you can if you want to. Then I'm going to take a look at what do I know the most about. Okay, so for plasma, I barely know anything. All I know is the mass fraction at the beginning. Same for red blood cells. So I can't really do much with either of those. But if I take a look at the tracer, I know a decent amount. I know that 100% of the stuff that is in stream 2 is the tracer. And I also know the mass fraction of tracer in stream 3. So I can go ahead and use that mass accounting equation, and let's see where that takes me next. Okay, so for the tracer, I'm going to go ahead and write these. So basically, this is what we have. And as usual, we can rewrite the right-hand side as the mass fraction times the total mass flow rate, right? And then this I already know because it's the same as the total mass flow rate in that stream, and because it was given to us by the problem, 17.21 grams per hour. And so if I simply divide this by the mass fraction of the tracer in that last stream, that's equal to the mass flow rate, which is in stream 3, which would be equal to 172.1 grams per hour. Okay, so now we have the mass flow rate in stream 3. And since I know this, I know stream 2 now, I can go ahead and use my total mass accounting equation to get there. So I'll go ahead and do that. Plus M2 minus M3 is equal to 0. Therefore, the mass flow rate in stream 1 is equal to M3 minus M2. Okay, and so that would be 172.1 grams per hour minus 17.21 grams per hour. So that's equal to 154.89 grams per hour. Okay, so but now let's look back up and make sure that's everything that you want us to know. So what the problem is asking me for is the flow rate of the patient's bloodstream containing blood. So like we said, that's the mass flow rate in one, except for, if you read carefully, it says give your answer in units of milliliters per hour. So what it really wants is a volumetric flow rate. And remember that we can always convert between these two using density. And by now, you should be really familiar with the fact, with the density of blood, which is approximated for most people as 1.056 grams per milliliter. If you forget that, remember that's always in your book, or you can Google it, etc. Okay, so I can simply use that, right? And just so you remember, these, to get the volumetric flow rate from the mass flow rate, the only thing you have to do is divide your mass flow rate by the density. So if we do that, what we would end up getting is now our actual final answer. And let me grab my calculator because I'm genuinely doing this problem for the first time. And that would be 146.67 milliliters per hour. As you can see, an important thing that I wanted to highlight with this problem is that you don't need to solve for every single accounting equation in order to find what it is that you're looking for, right? The other thing that I want you to notice is that it is really important to pay attention to exactly what the problem is asking you and the units. And lastly, that sometimes you'll be giving extra information that you in the end don't even end up needing to solve the problem. I hope that was helpful, and I'll see you in class.